The use of reinforced construction materials goes way back for centuries. The idea behind reinforced materials is to combine two or multiple materials of different properties and create a composite that has improved overall mechanical properties. The use of reinforced concrete is ubiquitous around the world. This can be in the form of steel rubber reinforcement, discrete fiber reinforcement, or laminated reinforcement. The same logic can be applied to soil reinforcement with the obvious difference that in reinforced concrete, the cement acts as the binding agent between the primary and secondary components, that is, the aggregates and the reinforcement. Soil, on the other hand, is comprised of discrete particles of varying shape, size, and generally has a low tensile and shear strength, and its characteristics may depend strongly on the environmental conditions. Therefore, the interaction between soil and the reinforcement member is solely by interface contact friction. The concept of soil reinforcement is not a novel idea. It is an ancient technique that was brought back in the 1960s. At present, soil reinforcement techniques are well established and in use across various applications such as improving bearing capacity, filters, and drainage control. We'll discuss more about the practical applications later in the video. My name is Chido Chashe. I'm a geotechnical engineer, and in this video, let's talk about fiber reinforced soils. You are watching Geotechs with Clements. I published a paper in 2021 titled The Influence of Discrete Fibers on Mechanical Responses of Reinforced Sand in Direct Shear Test. Like most engineering solutions, this idea was inspired from nature. You see, plant roots have a natural means of incorporating randomly orientated fiber inclusions in the soil, contributing to the stability of the soil mass by adding strength to the near surface soils in which the effective stress is low. What do I mean by this? When soil fails in shear, a shear plane is formed. What I discovered in my research is that the volume and angle of orientation of the reinforcement fibers has a direct influence on the strength and deformation characteristics of the soil. When fibers intercept the shear plane during failure, the shear stresses are transferred to the fibers. Tensile stress is then mobilized in the fibers and transferred to the surrounding soils through the frictional contact along the interface. As a result, the shear strength of the soil plus the tensile strength of the reinforcement fiber increases the overall strength. The implementation of fibers and geosynthetics in geotechnical engineering goes beyond improving structural performance. You see, the built environment sector is notorious for producing the highest carbon footprint, as highlighted in the United Nations Environmental Programme report, Building Materials and the Climate, Constructing a New Future. The building environment sector is by far the largest emitter of greenhouse gases, responsible for at least 37% of the global emissions. The reason I am bringing this up in a video seemingly focusing on soil reinforcement is to present the case for the wide adoption of this technique across the industry. One of the three agent pathways recommended in the report focuses on avoiding the extraction and production of raw materials by galvanizing a more circular economy, which requires building with less materials through better data-driven designs, while reusing buildings and recycled materials wherever feasible. Bear with me on this one. It will come full circle once I go through the following section. Earlier I mentioned the practical applications of soil reinforcement. This technique has been widely adopted in backfield slope stability and in both temporary and permanent pavement construction. In pavement construction, whether it's a rigid pavement or a flexible pavement, geosynthetics can be incorporated as part of the pavement structure. The advantage being that they can act as a layer separator and avoid aggregate penetration into the softer grade material. They can act as drains to remove water from the pavement structure and as hydraulic barriers to keep water outside of the structure, and also as a reinforcement, providing the mechanism like the one that I described earlier. The strength characteristics of geosynthetics can be guaranteed since the material is factory produced and tested in a controlled environment. Several studies have demonstrated the potential of using waste materials to improve the geotechnical properties and stability of soil. This means the geosynthetics can be manufactured from recycled municipal solid waste materials like plastics, wood, and clothes. Going back to the topic of sustainability benefits of using geosynthetic solutions, in roadway construction, they can be quantified in two different ways. The first and the most straightforward approach is to compare the embodied carbon of equivalent pavement structures at the end of construction. Equivalent pavement structures are those structures that have different structural components but the same expected performance and maintenance over the design period. For instance, in the case of base stabilization, a traditional unreinforced pavement structure could be equivalent to a reinforced structure with a thinner base layer. Both structures are expected to handle a certain volume of traffic over a certain period while maintaining a desired level of serviceability and hence equivalent. However, the embodied carbon of two equivalent structures is different owing to the different type and volume of materials used. So, let me simplify what this all means. We can quantify the carbon equivalence of different structures but with a similar function based on the design, construction, and maintenance information. In this case, a traditional pavement structure and a geosynthetic reinforced pavement structure. In a pavement structure, generally we have a subgrade, subbase, a base, and a surface layer. However, geosynthetic enhanced pavements tend to have a reduced profile than their traditional counterparts. The lesser volume of material used results directly in a lesser embodied carbon of constituent materials in the final structure. Let's think about it for a second. You see, geosynthetic enhanced pavements can allow the usage of poorer quality in situ materials and utilize the reinforcing strength of the geosynthetic layer, while traditional systems require high-grade construction aggregates which may not be available locally. The material has to be sourced from somewhere, and in most cases from quarries. This is not only expensive, but it also leads to the destruction of landscapes and causing pollution, therefore contributing to the increased embodied carbon. Geosynthetics are typically thin, flexible, and plate-like. Combined with my previous explanation of lower volumes of construction materials or locally available poorer quality materials, the total haulage or transportation of all materials to the project is usually lower in the case of geosynthetic enhanced pavements. There is also the issue of long-term maintenance, carbon reduction, and reduction of water usage in compaction that I will not go too much into. But as you can see, soil reinforcement is a more economical and environmentally friendly technical solution compared to the traditional means. I recently made a video on the geotechnical engineering of the moon. I recommend you go check it out after this video. In that video, I touched on some of the challenges and complexities that will be encountered. And if we are going to colonize the moon, I believe more research and development investment in reinforced soil techniques will provide viable solutions for lunar surface infrastructure development. Let me know what you think in the comment section below. I've been your host, Chido Chashe, and you've been watching Geotechs with Clements. Please leave a like and subscribe to the channel. Until next time.